is going to go down and reach some steady state RS. And C, suppose you start from 0 molecules of C, that's going to increase and become CS, which is the steady state C. Okay? And after that, they are not going to change. Does this make sense to you? So you start from 0R and 0, no, not 0R, R 0 amount of receptor and 0 amount of complex. So after a while, if you follow these dynamics, you'll see that R is going to decrease because you're losing free molecules, and there will be complex formation, and that's going to reach some steady state when there is no change of time. Like after that, it's all remain at the same value once you reach that steady state. And those values you can calculate by setting the left-hand side of these equations to 0, you can calculate exactly. But not the dynamic, like how this increases to the steady state, that you cannot calculate analytically. Okay? So the only possible way you can calculate such a behavior is through numerical solution. And let me first show it for first order ODEs. Okay. Suppose you have this form, dy dt equals f of yt. Okay? And you know, to solve first order equation, suppose this you can write as product of gy and ht. Suppose you separate the variables. Then this is the very first lecture where I started. You can do ht dt integration. Okay. This is simple separation of variable. But suppose your form is not that simple. Suppose you have fyt equals something more complicated, say sine y plus e to the power minus t. Then dy dt equals sine y plus e to the power minus t. Okay. Now, can you do this separation of variable solution for such an equation, like for this? Or any other method by which you can solve this? Yes? Any idea? So you see, in the general case, it's not that easy to solve analytically. And again, you need to do numerical solution. Okay? And the idea behind numerical solution is not that difficult. It is, so suppose your solution of some differential equation is ft. And ft has this form. Now let's take some time t, and after a small interval delta t, you have t plus delta t. Okay. And the function here was ft, and here ft plus delta t. And ft plus delta t can be written as, to some approximation, if delta t is really small, ft plus delta f over delta t times delta t. Okay. And delta f, so if I zoom this area, so the idea is you can approximate any curve by a straight line if they are sufficiently close. Okay, so that's the idea, that this is delta f and this is delta t. So you write ft plus delta t as delta f divided by delta t times delta t. This is permissible, okay? Because delta t cancels, you have delta f. So basically what I'm writing, ft plus delta t is ft plus delta f, correct? Now what is delta f over delta t? That's the idea. The idea is if delta t is small, so if you take delta t going to 0 limit, then you can write f t plus delta t as ft plus df dt dt. Okay, so that's the idea. So you are choosing delta t really small, so you can approximate this delta f over delta t simply by df dt, okay, by the derivative. In general, you should write ft plus delta t as f of t plus df dt delta t plus half d2f dt2 delta t square plus 1 by 3 factorial d3f dt3 delta t q this. Okay. So if delta t, depending on how small it is, you can keep up to first order, second order, third order like this. Okay. So the idea is you know the function at some point time t, and you want to calculate the functional value after some time t plus delta t. Now depending on delta t, how small or how large it is, you need to keep terms of the order of delta t square, delta t q like that. So suppose delta t is 1. Then what is delta t square? Of the order 1. Delta tq, that's also 1. And that means, can you ignore delta t square or delta tq compared to the first order term? No, because if delta t is of the order of 1, this is also of the order of 1, this is also of the order of 1, this is also of the order of 1. Okay. Now choose it smaller, 0.1 or 10 to the power minus 1. Okay. If that is the case, then delta t is of the order of 10 to the power minus 1, delta t square 10 to the power minus 2, delta tq 10 to the power minus 3, correct? Now, depending on how accurate you want your solution, suppose you want your solution accurate up to second decimal place. So you then ignore all these higher order terms and keep 10 to the minus 1 and 10 to the minus 2. Does this make sense? Now, if you increase the delta t even bigger, like delta t is 10 to the minus 2, this is 10 to the minus 2, this is 10 to the power minus 4, this is 10 to the power minus 6. So now if you want to keep accuracy up to 10 to the power minus 2, you can ignore this and this. Okay. So depending on what type of accuracy you want, so if you want accuracy on 10 to the minus 2, then you can ignore this and the cubic order term. So that's the basic idea behind doing numerical solution. Okay. So you get a differential equation and then you calculate this Taylor expansion. So this expansion is called Taylor expansion. Okay. And in the Taylor expansion, depending on what order term you want to keep and the accuracy, you choose your numerical solution scheme. So in the simplest scheme, which I call the Euler scheme, let me take the notation from the note, so it will be easier for you. You do y1, suppose your equation is dy dt equals g t yt, and you want to expand t0 plus h as yt0 plus dy dt at t0 times h. So h is the time step delta t. So this is time step delta t. Okay. Now this I can write y t0 plus h f t0 y0. Should I write? It should be g.